Hi there. Today we're going to take a short look at reinforcement learning with augmented data. This paper is by Michael Laskin, Kimin Lee, and others from UC Berkeley and NYU. So the reason why this is a short look is because I believe the statements made in the paper are quite short and small, but they are quite grandiose. So we'll dive into it. The paper basically combines two things: reinforcement learning and data augmentation. Now, reinforcement learning, we've talked about a number of times. It's basically where an agent is in a world and has to learn to solve an optimization problem by repeatedly interacting with the world. You can see here, for example, this is the walker task, where this walker thing, it has 2 feet and basically needs to stand upright and walk for a number of steps. The further you go, the better. So by repeatedly trying this and getting better and better at it, that is reinforcement learning. The second part is the data augmentation. Now, data augmentation is a pretty standard practice in supervised learning. What does it mean? So if you have a supervised learning task, for example, an image classification task, here is a picture of a cat and the label is cat, then you can feed this through your neural network, right, to arrive at a loss. And but you only have so many pictures, right? You have a database and maybe you have, I don't know, 1 million images. Okay. Usually what people do is they go, let's say, a number of times, like 20 or 50 times through that database to basically have the model learn each image multiple times. But what turns out to be more successful is if you do data augmentation. That means you have an in-between layer right here that takes this image and modifies it in some small way. This could be, for example, it blocks out part of the image. So it simply blocks out this square here. And then you feed that through the model. And then the next time the image comes up, it does something different. For example, it randomly crops the image to only the top right part here. And then the next time it does a bit of a color jitter. And then the next time it goes to grayscale and so on. So supervised learning has found data augmentation to be quite beneficial because not only do you make the model learn what this picture is, but you also make the model kind of learn some small variations of that picture where you can be pretty sure they would not change the label, so you would not feed the model false information. That generally makes it more robust to test time discrepancies. So this paper has basically claims. If you want to do reinforcement learning, if you simply do data augmentation with the input data to that reinforcement learning, it works much, much, much better. Now, of course, we can expect, since in supervised learning this is a general trick, that it would do something for reinforcement learning as well. But this paper basically claims that this one plugin, like here, so this is basically, you plug this into your pipeline in reinforcement learning, this is basically as much of a gain as pretty much the last 5 years of research on reinforcement learning on these things. So let's dive into it. This paper proposes just what I said. Just plug in the data augmentation and then do reinforcement learning on the augmented data. They use these data augmentations. So crop, we've already discussed, it's a random crop. Grayscale means that the picture goes to gray, black and white with a certain probability. Cutout means that there's a little patch missing, like I said. Cutout color, the same but in a random color. Flip means you flip the image horizontally or vertically according to a random probability. Rotate is the same, but you, instead of flip, you rotate it. Random conv means you randomly convolve it with a filter. In this case, some red or blue or yellow filters. And color jitter means that you kind of jitter around the colors in a sort of way that doesn't mess up the image too much. So you basically just kind of change the colors on the image, but the overall image still looks the same. The only thing you have to pay attention to is that, so in your reinforcement learning pipeline, usually if you have a walker like this, what you want to do is you have your network here, and then you have, you know, your policy and your value function. If you don't know what these are, I've treated them many times in reinforcement learning videos. What you want to do is you simply don't want to take this one current observation in here, but sometimes you want to take kind of the stacked of the last few frames, so that the model kind of gets an idea what happened during, let's say, the last 1 second, right? So it can determine in this walker, for example, it's not only important where the legs are, which are up here right now, it is also important their momentum, how they're moving, right? And you can determine that from the last few frames. So sometimes it's beneficial to feed the last few frames, and they say the important thing here is that these augmentations are applied consistently across the stacked frames. So basically you select on an augmentation and on the scale of that augmentation, and then you apply it to these stacked frames all the same. And then in the next forward pass, you have a different set of stacked frames. Then you can decide on a different augmentation. So that's basically the only difference between the supervised setting and this setting, is that you have to consistently apply the augmentation. And you have to consistently apply this here and during training. So they formulate the classic proximal policy optimization here, which is an actor-critic method. And the only time you have to really pay attention is when you plug the observation into these models here, right here, then it needs to be the same augmentation. Sorry, the same observation. So that means the observation augmented with the same data, with the same augmentation procedures. All right, getting it together. Cool. So when you do this, when you do that, let's say, when applying RAD, which is the random data augmentation, to SAC, which is soft actor critic, right? Our data augmentations are applied to the observation passed to Q and pi. So, sorry, this is the thing up here. This is soft actor critic, which is a state-of-the-art off-policy algorithm for continuous control problems. And also you have to pay attention that when you feed the observations, they're the same observations, like here and here. And then proximal policy optimization is a state-of-the-art on-policy algorithm for learning a continuous or discrete control policy. Okay, so as I said, they simply drop this in there, and then it turns out they outperform or match performance of many, many baselines. Here you can see curl. I've made a video on curl, which is another way of augmenting or pre-training for reinforcement learning. Then state-of-the-art things like Planet or Dreamer, I've made a video on Dreamer as well. And then Pixel SAC and State SAC is sort of a cheating algorithm because it has access to the state, whereas all the other methods only have access to the pixels. And you can see that the data augmentation method, which is basically just plain RL, plain PPO or SAC, plus the data augmentation, outperforms in many times all of these other baselines. Now, here is a criticism of me. They never investigate, they simply say, wow, this reaches the same performance or outperforms these other methods. Now, so it's the state-of-the-art algorithm. It's important to note here that this is on the DM Control 100K and 500K benchmarks, which means that there's a limit on the number of, I believe, frames from these control tasks that you get. So you either get 100K or you get 500K frames. So the difficulty is learning from limited data. It's not state-of-the-art reinforcement learning method overall. It is the state-of-the-art on this particular task, on learning from limited data. Now, while I can believe that the augmentation would help here, it is completely unclear whether or not the augmentation gives the same benefits as like something like Dreamer, or whether the benefits from Dreamer and the benefits from data augmentation are completely orthogonal. So in this paper, given that the claim is so simple that they make, I would expect like an investigation. What happens if I do Dreamer plus the data augmentation? Maybe they've done it somewhere and I just haven't seen it, but it just seems like they put this on the basic RL algorithm, and then they claim, well, look here, it works well, but they never show that. So it could be that Dreamer, all this architecture, what it simply does is basically recover these gains that you could get by data augmentation, or it could be that it actually does something different, but just reaches the same amount of gain, right? It just reaches the same amount in improvement, and by combining them, you could improve it further. So not just to get like a better number, but combining the two would actually give a lot of hints as to whether or not this augmentation works in line with the other methods, or whether the other methods are really doing something meaningfully different or not. But this is just not done here. And so they go into a question of which data augmentations contribute the most, and they get to the point where they say random crop is extremely effective. So they have this table here where they just basically combine two augmentations, and so you see, so for example, this thing here means that you apply grayscale and then the rotate augmentation, and that gets you to whatever 300 points in this walker. If you apply crop and then crop, it gets you to 920 points and beats everything else. So they say, okay, crop is the most effective, and I have the sneaking suspicion that these augmentations are so effective simply because of how we set up these tasks, right? These reinforcement learning tasks, they don't tend to be a real world. They tend to be somewhat simulated. And as you can see here, the image is pretty clear, so you can pretty clearly see that here is the thing. There's no natural background or whatnot. It's procedurally generated, right? There are these stars that could confuse the model a bit, but still, it is so easy visually, this task, that I'm going to guess the whole reason why these image augmentations help is simply because of the way these reinforcement learning tasks right now are set up. And I would guess that if we had reinforcement learning in something like the real world, that the image augmentation methods would help in about the way they help unsupervised tasks in the same data, for example, ImageNet. So that is my sneaking suspicion. And this paper, I want to say it sort of overclaims its how absolutely great this works. Of course, it works great on these things, but I think there needs to be an investigation of why, right? So here they have some attention maps on where the algorithm focuses, and you can see when there's no data augmentation, it sort of focuses on good points, but when you do crop, it focuses on this ridge here, which makes sense, right? Because that's the thing that needs to be kind of vertical in order for the walker to be stable. And if you do other things, then you can see it doesn't really focus. It focuses on different things. So the crop method seems to make the model focus on the most important part of the image. And as the same with the cheetah task here. So if you don't do augmentation, and some of the augmentation, you can see that it actually focuses on some of these background stars, whereas in the cropped version, it focuses on not on the stars, but actually on the cheetah as a whole, which probably makes sense. Now, again, I have a bit of a worry with these kinds of experiments, because we already know that crop will give you a much better score, right? So who's to say that if we could train this thing here to the same score, it wouldn't be paying attention to the same part. What they're trying to make clear here is that it is dependent on the particular type of data augmentation that the model gets a better grip on the input, but it is not really a valid comparison if we know that the crop agent performs a better score. And it could simply be that that's the reason why the attention is better, right? That it is actually solving the problem better. So, I mean, of course, the fact that it's working better is due to the fact that you have crop augmented the data, but the fact that it is focusing on the correct parts is not a property of the crop augmentation, but a property of the fact that it reaches a higher score. That was a long-winded complaint, but I hope you get what I mean here. The last thing they do is they investigate generalization performance. So improving generalization on this OpenAI ProcGen. Now, as I understand it, this is a reinforcement learning task or a suite of tasks where you have procedurally generated levels. So you can sort of train on a bunch of levels and then test the generalization to new levels that you haven't seen before. So there's Jumper here and Star Pilot. So they seem like this, like a jump and run game, or Big Fish. I don't even know what you have to do in Big Fish, but you can see that the levels seen here, this is one example, and unseen. So in this example, the background is very different, and I'm going to guess in the jumper thing, not only is the background different, but also the kind of generated level, how you have to jump, is quite different. So they investigate whether or not a agent trained on only the seen ones can generalize to the unseen ones. And this table presents the results. And as you can see, the RAD with the crop or with other things outperform the pixel-based PPOs. Now, there is some nuance to this table here. First of all, you can see that this crop thing is now only the winner in one of these three tasks, right? In the Big Fish thing. There is another augmentation technique here that wins over at Star Pilot, but you can see the difference is not that high. And in the jumper, with 200 levels, so this is 100 or 200 levels, the original method is even the best. So here again, I believe this is evidence that it is very much an interaction of these augmentations with the way the task is set up, and not the augmentations themselves or the fact that you're augmenting. For example, if we look at this Big Fish, we've seen, okay, what seems to change here is mainly the background, whereas in the jumper example, the entire level structure seems to change. So then the augmentation all of a sudden is not super effective anymore. Actually hurts, right? So I'm just not super convinced by the claims they're making here. And one of the claims I find is, in particular, RAD with random crop achieves. No, wait, this point down here. Achieves 55.8% gain over pixel-based PPO. Okay. Trained with 100 training levels outperforms the pixel-based PPO with 200 training levels on both Big Fish and Star Pilot environment. This shows that data augmentation can be more effective in learning generalizable representations compared to simply increasing the number of training environments. This statement, so again, why do you compare two different things if you don't show that maybe they're orthogonal? In fact, they are probably orthogonal, because even on the 200 levels, you gain over the pixel-based PPO, right? So why the comparison? And then second of all, So here we see on the 100 levels, this method is better than the pixel-based PPO. And then they claim that, okay, they are even better on 100 levels than the pixel-based PPO on 200 levels. And why that is true, if A is bigger than B, then probably A is going to be bigger than B plus some epsilon, and right, and that doesn't. I just think that doesn't really warrant their statement where they say, "Oh, look, this is even better." So as if the 100 levels of additional training were the standard measure of more data. Like if there is going to be, if you're better at the beginning, there's going to be a certain amount of data where you're still better than the other method with more data. I don't find this super duper surprising, but they make a big claim here out of this. All right, so in conclusion, I hope I'm not too harsh on this paper. It is a cool paper, and of course it is cool findings, but I have a big suspicion that the augmentation here works so well simply because of how we set up these RL tasks, because they're visually quite, let's say, easy, and therefore these augmentations that are also our sort of easy abstractions of when an image is visually similar, because all of these things, right, to us as humans, we say, probably it doesn't change anything if we just rotate the image. And this is our prejudice, and we built this prejudice into these simulators for the RL tasks. So they will match up extremely well with these augmentations. And that's the reason I believe these things work, and maybe not as much the fact that you're augmenting. Okay, well, if you like this video, I invite you to check out the paper, subscribe to this channel, tell all your friends about it, and leave a like and a comment. Thank you very much, and bye-bye.